Very good morning, students.
Good morning.
Good morning.
Good morning, sir.
Good morning, sir.
Good morning, all of you. So let us start with the discussion. Last class, if you try to recall the concepts, whatever we have discussed, they were all about structural isomerism. In the stereoisomerism, we have discussed about geometrical isomerism as well as conformational isomerism. Yes or no? So the isomerism is actually divided into two parts: structural and stereo. Structural, chain, position, ring chain, tautomerism, metamerism, functional group. Tautomerism will be discussed in the GOC part, as I have mentioned. In the configurational isomerism, we have geometrical and optical. In the geometrical, you have cis trans, EZ, and syn anti. So that geometrical part, as well as conformational isomerism, which are due to rotation of carbon-carbon single bond, along with the different cases where intramolecular hydrogen bonding is also present. Gauge forms are how stabilized. All those points we have studied. Now let us start with optical activity, students. The next part in isomerism is optical isomerism. So what is optical isomerism or optical activity? Compounds having same molecular formula, same structural formula, different 3D arrangement, but different behavior towards plane polarized light. Understand this carefully. If a compound can rotate the plane polarized light by a clockwise direction or an anti-clockwise direction, then that particular compound is said to be optically active in nature. And the isomers of that particular compound, they are said to be optical isomers. What is optical isomerism? Compounds which can rotate the plane polarized light, which in short form is written as PPL. If an organic compound is there, of course, most of the organic compounds may be present in the solid state. So we have to take a particular solvent and dissolve that organic solvent. So we have a small tube known as cuvette tube. In this cuvette, we will be adding the desired organic solvent. Organic solvent has to be chosen in such a way such that the organic compound is going to be dissolved. Whenever you are choosing the dissolution, you have to follow the principle like dissolves in like. That is, polar solvent dissolves in polar solute dissolves in polar solvent, non-polar solute dissolves in non-polar solvent. Like dissolves in like. Yes or no? You have to add the organic compound. Organic compound, whenever it is added to a particular organic solvent, it will be dissolved. Now we have a solution of that particular organic compound. Now we are passing this plane polarized light. Light, if you take initially from the source of light, light has an intensity in all the directions. Light has intensity in all directions. Whenever you pass that to a prism, we will be getting a plane polarized light. That means whenever you pass the electromagnetic radiation by a polarizer, initially light has intensity in all the directions. Now the intensity will be only in one direction. That is nothing but a plane polarized light. That plane polarized light, whenever it is passed through polarimeter tube having a compound solution. This is a polarimeter tube which I have explained here. That is organic compound added to a particular solvent, and through that particular solvent the plane polarized light has been passed. There are three cases possible. What are the three cases? The plane polarized light, which was initially present in this fashion, whose intensity was in this direction, that has been rotated by an angle theta in the clockwise direction. Clockwise, it has rotated in the angle theta in the anti-clockwise direction. The third case is no rotation happened. So when a plane polarized light rotates in the clockwise direction by some angle theta, it is said to be dextrorotatory or plus or D or optically active. D stands for dextrorotatory. If it rotates in the anti-clockwise direction, it stands for minus or L, which is again optically active. If you do not rotate the plane polarized light, it is said to be optically inactive. We are going to write down what are D and L in the upcoming slides, but you can understand, if the plane polarized light is rotated by an angle theta either in the clockwise or in the anti-clockwise direction after passing through the organic compound, then that particular compound is said to be optically active. If the rotation is in the clockwise direction, then it is said to be dextrorotatory, indicated with a plus sign. If it is in the anti-clockwise direction, it is levorotatory, indicated in the minus sign. And D and L, here whatever you are using, they are small. Small d and small l indicates optical rotation, that is dextrorotatory and levorotatory. If I write capital D and capital L, they are configurations. Okay, we'll be looking at them, capital D, capital L configurations also. Small d, small l indicates optical rotation direction, that is clockwise direction or anti-clockwise direction. Capital D, capital L have completely different meaning. Small d, small l, optical activity. Capital D, capital L, configurations of that particular molecules. Is that clear, student? Definition?
Yes, sir.
So the simple logic is, we have some organic compound, whether it is optically active or not, I have to find out how. I will be choosing a particular solvent, add that organic solvent, make it soluble in that, and whatever the tube I have, through that tube I will be passing the plane polarized light. Plane polarized light have an intensity in this direction. Let us say this is an organic compound tube. After passing, if it rotates in the clockwise or in the anti-clockwise direction, it is said to be optically active. You may ask a simple question, sir, everything is fine, but we are not given with the apparatus setup. Experimental setup is not given to you. They will give you the molecule to you. You have to figure out whether the compound is optically active or not without performing the experiment. Yes or no? So that is the main logic involved here. So how to figure out whether the molecules are going to be optically active or not? By looking at the structures of the molecules. In that perspective, the first idea what people got is regarding chirality. The molecules which possess chiral carbons, they are found to be optically active. But later on, the definition has been modified also. As of now, the complete picture we can say, if the molecule possesses, if the molecule or compound, organic compound possesses one chiral carbon, only one chiral carbon, it is said to be optically active, directly no issues at all, optically active. But ring flipping of tertiary amines, even though we have only one chiral carbon in quaternary amines, ring flipping happens, it is found to be optically inactive. Exception of ring flipping greater than one chiral center. Greater than one chiral center of chiral carbon. In that case, we have to look at, whenever we have a single chiral carbon, we can say it is optically active, unless and until if the given compound is a quaternary amine where ring flipping happens. In that case, even though we have one chiral carbon, it is optically inactive. If you have greater than one chiral carbon, you have to check out elements of symmetry. Elements of symmetry. Based on elements of symmetry only, we have to decide what are the elements of symmetry we have.
Plane of symmetry and center of symmetry.
Yeah, and we also have axis of symmetry, but we generally discuss about axis of symmetry and the molecules involving that, because that is of higher level. So one chiral carbon means optically active, exception of ring flipping. Greater than one chiral carbon means you have to look at elements of symmetry. In that, you have to look at a plane of symmetry and center of symmetry. And if you have zero chiral carbon, then also chirality can be existing or not. Any molecules which do not have a chiral carbon but still it is optically active? Anyone? Do you know any chiral carbons which is optically active? Yes, Faizan?
Glucose.
Glucose do not have chiral carbon. Glucose is optically active or not? Look at the carbon atoms in the Fischer position itself. You know it. Yes or no?
Yes.
So zero chiral carbon compounds also found to be optically active, which are like allenes, biphenyls, alkylides. We'll discuss all of this. Okay. We'll discuss all of this. First, you have to know a complete idea. So optical activity is the ability to rotate the plane polarized light. How to figure out whether the compound is optically active or not? If we have only one chiral carbon, it is directly optically active, exception of quaternary amines where ring flipping occurs. Greater than one chiral center means you have to check out elements of symmetry. If you have elements of symmetry like plane of symmetry or center of symmetry, if a compound contains a plane of symmetry or center of symmetry, it is optically inactive. Optically inactive. Even though there is no chiral center, there are some compounds which are optically active, which are also called as allenes, biphenyls, alkylides. So we are going to look at one by one. So we have discussed about chiral carbon. What is a chiral carbon? First of all, a carbon which is actually connected to 4 different groups. Let us start with the discussion after the definitions. So this is light source. The light source is passed to polarizer, and you have a polarimeter tube, and then we have an analyzer. So you can just look at the way the rotation is actually happening. Yes or no? From the light source, whatever the plane polarized light you are getting, from the light source, whatever the light you are getting, after passing through polarizer, you are getting the plane polarized light. That the plane polarized light, after passing through polarimeter tube, it has been rotated in the clockwise direction. Another light source, another polarizer. So now it has been rotated in the anti-clockwise direction. Yes or no? So this is the polarimeter tube, which is also called as a cuvette tube, where you have organic compound. So if it is rotating in the clockwise direction, it is said to be dextrorotatory. Anti-clockwise means levorotatory. Yes or no? If a molecule rotates plane polarized light in any direction, either clockwise or anti-clockwise, it will be considered optically active. It can rotate in the clockwise direction or anti-clockwise direction. It does not matter. If it can rotate the plane polarized light, it is optically active. If net rotation of plane polarized light is 0, then it will be considered optically inactive. If net rotation is 0 means optically inactive. Clockwise rotation means dextrorotatory, which is also indicated with small d or plus sign. Anti-clockwise rotation means levorotatory, which is also indicated with the L or minus sign. And these are the factors on which your angle of rotation depends. That is, we are all saying like the plane polarized is rotated by an angle theta. That angle of rotation will be depending upon length of polarimeter tube. Length of polarimeter tube means how much you have taken the organic compound. That much the rotation will be present. Wavelength of the initial light source, the wavelength of the light, whatever you have used, that is also taken into account. Concentration of solution in gram per ml, and temperature in degree. That is, if we vary the temperature also, the optical rotation is going to be changing. So these are all the factors on which angle of rotation is going to be changing. Is that clear, students?
Yes.
Yes, right. Yeah, chiral center, chiral atom or asymmetric atom. sp3 hybridized atom attached with the 4 different groups. sp3 hybridized, the carbon atom should be sp3 hybridized. That means it is connected with only single bonds. sp3 hybridized atom attached with the 4 different atoms or groups is said to be chiral atom or asymmetric atom. So like this carbon, which is connected to hydrogen OH, CH3 and COH, that is said to be chiral. Chiral carbons are indicated with a star mark generally. Chiral atom or chiral carbon, they were indicated with some star mark, asterisk or star. Try to figure out, find the number of chiral atoms or chiral carbon centers present in this particular molecule. How many chiral carbons are there here? Find the number of chiral centers present in the, how many?
Two.
Two. Look carefully, Me is also methyl only.
One.
Yes or no? Me, they have written, although Me is written, it is also CH3. So this CH3, 3 hydrogens connected, not a chiral. Methyl means CH3, not a chiral. CH, methyl, not a chiral. CH, Cl, this other group, and this are different group. So this is one chiral carbon. CH2, CH3, a chiral. So only one chiral carbon. Right? One chiral center. Try to figure out here. CH3, CHBr, CHCl, CHOH, CH3. This is achiral CH3, CHBr. Like one is methyl, other is hydrogen, other is bromine, other side other bulky group. This is chiral. To this carbon, one is hydrogen, one is chlorine, other side CHOH, CH3, this side CHBr. So 3 chiral. So all these are going to be chiral. So how many chiral carbons? 3 chiral carbons. Find the number of chiral center present in the given molecule. How many chiral centers are there in this particular molecule? Just try to figure out the carbons which are connected with different groups. Here we have CH2. CH2 means 2 hydrogen, not a chiral. CH2 not a chiral. CH2 not a chiral. CH2 not a chiral. CH2 not a chiral. So I have eliminated all the CH2 groups. Remaining left out methyl eliminated CH3, 3 hydrogens. Look at this carbon. This carbon connected to methyl group. Other side I have CH which is a fused with other ring. Other side I have CH2 and one more is hydrogen. So all 4 different groups. So star mark. Look at this particular carbon. This carbon is connected to CH2, then CHCOH. It is connected to CHMe, CHMe. So, and one hydrogen, and other side is another bridge, like another carbon which is connected in the 2 rings or fused carbon. It is also connected with 2 different, all different or 4 different groups. So chiral. Same way here, hydrogen is one group, other side this carbon, other side CHOH, other side CH2. So all 4 different. So chiral. What about the CHOH? Chiral, because hydrogen OH, others 2 different sides, 2 different groups are there. So all 4 different groups. So chiral. CH2 achiral. Look at this carbon. This carbon is connected with COH. CH2, CH2 are matching. But just look at the next. After CH2 we have CHOH. After CH2 we have carbon connected in the with the other ring. So they are again different. So this is also going to be chiral. So how many are there? 1, 2, 3, 4, 5. 5 chiral carbons are going to be present here. Okay. Yes. Find the number of chiral centers present in the given molecule. How many chiral centers are there here? SAME, S double bond O, ET. ET means ethyl group, that is C2H5. C2H5 means CH2, CH3, CH2, 2 hydrogens, CH3, 3 hydrogens. So that is not chiral. But sulfur has all 4 different groups or not, including the methyl. Methyl, ethyl, S double bond O, and lone pair, including everything. Sulfur has a chiral center. Sulfur is the chiral center. Representation of a tetrahedral carbon. Okay. So last class, what type of representations we have studied, students? Last class, if you remember, out of Sawhorse, Newman, Vegdash, and Fisher, what type of representations you have studied in the conformations?
Sawhorse and Newman.
Yeah, Sawhorse and Newmans.
Sawhorse.
Very good. So we also have Vegdash formula. That is a 3D representation of molecule. In the 3D representation of molecule, if you have carbon connected with bromine, chlorine, iodine, and fluorine, yes or no? In this representation, 2 groups are present in the plane represented by a normal line. Whatever the dark normal line we have written, like carbon chlorine bond, carbon bromine bond, carbon, chlorine, and bromine, they are lying in the same plane. That is plane of this particular screen. One group is towards the observer, solid wedge, and the other group is away from the observer, that is dash. The group which is towards the observer, that is iodine. Yes or no? It is represented with solid wedge. Like this molecule is there. I have a plane like this. I have a paper like this. In this paper only we have carbon, chlorine, carbon, bromine bond. The iodine is actually towards me. The iodine was somewhat like this, towards me. The fluorine was towards you. The fluorine was pointing towards you. So carbon, bromine, chlorine, they were in the plane. Carbon, iodine is towards our side. Carbon, fluorine is towards your side. That is towards the observer and away from the observer. They were represented by wedge projections and dash lines. Understood? So this is how the 3D molecule is actually going to be present. That is the wedge dash formula or 3D representation. And you can just look at the molecule. Because of molecular motion, all the molecule is not static, it is continuously rotating. Yes or no? And this is how you can understand how the tetrahedral molecule is there. Fisher projection, the next kind of projection is like representation is Fisher projection. This is a projection, it is a 2D projection of a 3D structure. Like 3-dimensional structure I cannot draw on a 2-dimensional screen. Whatever the screen I am writing, this is 2 dimensions only, it is not 3 dimensions. So this is a projection 2D of, it is a 2D projection of 3D structure. Any structure, whatever you are going to look at, is 3D nature or not? Like this water bottle, yes or no? This water bottle, this particular remote, if all are 3D structures, like we have length, breadth, and height also. So I cannot draw the 3D structure on a 2D screen or a 2D board. So what we can do is we can actually project the 3D structure. Like if I have a sphere, if I project the sphere, what I will be getting? If I project the sphere on a paper, I will be getting a circle. Yes or no? So similar to that, Fisher projection or 2D, it is a 2D projection of a 3D structure. In this projection, molecule is kept in such a way such that the groups are seen on vertical line. Like two groups are seen on vertical line and two groups are seen on horizontal line. Groups at horizontal lines, they will be towards the observer. Groups at vertical lines, they will be away from the observer. If you try to look at the molecule, like CH3, CHOH, COH, look at this carbon, CH3, achiral. This carbon, CHOH, CH3, COH, four different groups chiral. COH, again it is sp2 hybridized carbon, so achiral. So if you try to represent this molecule, like carbon connected with COH, OH, H and CH3, like two groups are represented in the horizontal line and two groups are represented in the vertical line. Now look at the molecule, students. The groups at horizontal lines, they will be towards the observer. Horizontal line, whatever the groups you have, that is OH and H, they are towards you. That is solid wedge. And the groups at the vertical line, they will be away from you. COH and CH3. Understood this or not? Fisher projection is a two-dimensional representation of a three-dimensional molecule. Since the screen is the two-dimensional in nature, I cannot draw the 3D molecule, so that I have to represent the 3D molecule in the 2D plane. Like if you have a single point, what is the number of dimensions for single point you have? If I have only one point, it is having how many dimensions?
One dimension.
Point is one dimensional. What about line then? If I have a line, straight line.
Point two dimensional, line one dimensional.
If I have plane, paper,
Two
Dimensional.
Two dimensional.
then point is also two-dimensional and paper is also two-dimensional.
Point is 3-dimensional.
Point is three-dimensional. Then what about cube?
Three dimensional.
So point and cube are same then. Point has no dimension, zero dimensions. Any point in space, no dimension, no. It's just a point. It is not moving in the x direction or y direction or z direction. Line, it can move in the one direction only. It is one dimensional in nature. How a line is obtained? How a line is obtained?
Connecting points.
Connecting infinite number of points. So zero dimensional points, if you try to add infinite number, you will be getting one dimensional line. How a plane is obtained? Infinite number of lines if you try to connect. This is one line, another line, like that. Infinite number of lines if you try to connect, you will get two-dimensional plane. How a cube is obtained? Cube or cuboid, whatever it is.
Connecting plane.
Connecting infinite number of planes, you can generate three-dimensional cube. Do we know about fourth dimension? Anyone knew about fourth dimension? Fourth dimension is actually time. Okay, we don't have in our syllabus, but I'm just saying fourth dimension is the time. So like the events. So now at time 10:25 it was 10:25 minutes and some seconds and some milliseconds. At that particular time, I am in this particular room teaching you guys. Like that, I may be in a particular position, you all may be in a particular position. If I take a picture of that particular scenario at a particular instant of time, you will get one event. Immediate next moment, I can take another picture. Like you can take photos, right? All those photos, whatever you have taken at different time intervals, if you can just place all of them. The fourth dimension is actually a time. If you try to arrange the events happening in the three-dimensional scenario, like if you repeat the three-dimensional events at a different time intervals, then you will get the fourth dimension time, which is known as tesseract. So anyways, this is how you have to know about the dimensions. This is what you have to know. Zero dimensional points, if you try to repeat, you will get one dimensional line. One dimensional line, if you try to repeat, you will get two dimensional planes. Two dimensional planes, if you repeat, you will get three dimensional structures like cuboids. And the fourth dimension is going to be time. If you try to take the movements captured at every time interval, and if you arrange them, then you will be getting the fourth dimension. You might have seen that in some movies as well, time travel movies. Interstellar, I have seen how many? Anyone seen the movie Interstellar? At last, he
Yes.
will be actually assessing all the events, right? That is nothing but the
Yes,
fourth
sir.
dimension, which is nothing but tesseract. Like he can access the event which has happened past. He is also able to see all the events, whatever happened in his life. So that is nothing but all the three-dimensional events placed in such a way such that you can access anything. But for humans, that is not possible. It is just a science fiction. So that is nothing but the fourth dimension. Fourth dimension is going to be time. And why I'm explaining all these dimensions means the Fisher projection is actually a two-dimensional projection of a three-dimensional molecule, right? Look at the structures. Okay, any compound of which mirror image is non-superimposable on it, or compound which has no symmetry element, that is said to be chiral molecule. Like if you have C2H5, C, CH3, HOH, if you try to take the mirror image, you are getting what? Mirror, if you just keep a plane mirror, not a concave mirror or convex mirror as used in the ray optics, you just keep a plane mirror. When you try to keep a plane mirror, the hydrogen which is supposed to be away, that will be same. Like you stand in front of a mirror, you will get a mirror image, right? Any compound of which mirror image is not superimposable on it, the mirror image and the original object and the mirror image, if they are not superimposable to each other, then that particular compound is said to be having chirality, chiral molecule. Chirality is the essential condition. Chirality is the essential condition for optically active. Optical activity, optically active compounds should possess chirality. Compounds should possess chirality. Chirality does not mean chiral carbon. Understand this. Chirality means having non-superimposable mirror images. Having non-superimposable mirror images. Chirality means it does not always means the compound should contain chiral carbons. Chirality is a case where we have non-superimposable mirror images. Okay. Condition for optical activity is molecule should be chiral. Molecule should be chiral or it should possess chirality. The molecule should be chiral or it should possess chirality means it does not mean it has chiral carbons always. There are some molecules without any chiral carbons. Without any chiral carbon, they are optically active. There are some molecules which having chiral carbons but optically inactive. Although we have chiral carbon, that does not mean it is optically active, because if we have a superimposable mirror images, like if mirror images are superimposable on each other, then they are said to be achiral in nature. So to understand all these students, we have to look at elements of symmetry. Once we go with the elements of symmetry, you will get the idea. Yes or no? Look at an object that cannot be superimposed on its mirror image is called chiral. An object that cannot be superimposed is called chiral. Like you have two hands or 2 feet, chiral objects, non-superimposable mirror images. If you have two glasses or two circles, non-chiral objects, like they are superimposable on each other. Superimposable means I have one hand here. If I keep a plane mirror, I'll be getting respective mirror image. If I remove this and just post it on the other, if they are exactly superimposable to each other, if they are exactly lying fall on each other, then they are said to be superimposable. If that is not the scenario, they are like if you just remove one glass and try to keep it on the other glass, they are found to be superimposable, right? Superimposable mirror image means non-chiral objects. Right, students? Elements of symmetry, presence or absence of chiral carbon, not necessary condition for optical activity. Presence or absence of chiral carbon is not a necessary condition for optical activity. The necessary condition for optically active for optical activity is the absence of elements of symmetry. There are two elements of symmetry, plane of symmetry and center of symmetry. Elements of symmetry should not be present. Why? If a molecule is there which has plane of symmetry, in the molecule like compound is there which has a plane of symmetry. If a molecule possesses plane of symmetry, like let us say this much is the bigger molecule. If I have this is as a plane of symmetry, then in this part, whatever the part we have on this side, that can rotate the plane polarized light by an angle theta in the clockwise direction, let us say. Then the other part which is symmetrical, that will rotate by an angle theta exactly, but in the anti-clockwise direction. If a molecule possesses a plane of symmetry, one part of the molecule is going to be nullifying the optical rotation of the other part. So as a whole, what is molecule? Net rotation exhibited by molecule is plus theta plus of minus theta. That is 0. So whenever the molecule possesses plane of symmetry, the molecule is said to be optically inactive. Not only plane of symmetry, if it also possesses element center of symmetry, in that case also it is optically inactive. If elements of symmetry are present, if plane of symmetry or center of symmetry are present, molecule is optically inactive due to internal compensation or external compensation. Like within the same compound, one part of the molecule is compensating the optical rotation of other part. So it is said to be internal compensation or external compensation.
Internal.
Internal.
Compensation. If plane of symmetry or center of symmetry are present, molecule is optically inactive due to internal compensation, and such molecules are called as what are those called as? Meso compounds. Meso compounds are optically inactive due to internal compensation. There are another set. If I take two optical isomers, one is rotating clockwise direction, other is rotating anti-clockwise direction, in equimolar quantity, and add them to generate a mixture, that mixture is said to be a racemic mixture. A racemic mixture is also optically inactive. Why? Because one compound is rotating theta in the clockwise, other is rotating theta in the anti-clockwise. Net rotation is 0. Racemic mixture is also optically inactive, but due to internal compensation or external compensation. External compensation, because the compensation is happening between one molecule and the other molecule. If the compensation happens within the molecule, then it is said to be optically inactive due to internal compensation, and such molecules are said to be meso compounds. If the compensation happens from two molecules, then that is said to be the case of racemic mixture. Okay, right? Plane of symmetry. What is the plane of symmetry first? It is an imaginary plane which divides molecule into two equal halves. An imaginary plane which divides molecule into two equal halves, that is known as plane of symmetry. Both parts should be mirror images. If a plane of symmetry is present, then molecule will be optically inactive. Like initially we have a figure like this, and I have taken a plane like this. As or no, if I divided that particular figure using this plane, these both parts are going to be symmetrical to each other. So plane of symmetry is actually present. If plane of symmetry is present, molecule is going to be optically inactive. So out of these four compounds which has plane of symmetry, which do not have plane of symmetry, try to figure out. CH4, CH3, Cl, CH2, ClF, CH, Cl, FBr. CH4 has plane of symmetry or not?
Yes, sir.
Yes.
CH3, Cl,
Yes, sir.
No, sir.
No, sir.
CH2, ClF?
No, sir.
No, sir.
No. So whenever you have two compounds which are same, always there will be a plane of symmetry. Check it out. Like CH4, you have no doubt, because I can break the molecule or cut the molecule in such a way. CH3Cl also I can cut in this fashion. CH2Clf I can cut in this fashion or not. Both are symmetrical. You can check. CHClFbr. Here, if I try to cut, I am not going to have a plane of symmetry. So here in these molecules, plane of symmetry is present. And in the fourth molecule, no plane of symmetry. No plane of symmetry. So it is going to be optically, and no center of symmetry also. So this compound is said to be optically active. Remaining three are optically inactive. Try to find out which of the following has plane of symmetry. Does this have plane of symmetry?
No, sir.
All four groups are different: hydrogen, fluorine, chlorine, bromine. So no plane of symmetry. Which of the following has plane of symmetry? This compound has a plane of symmetry or not?
Yes.
Sir.
Yes.
Can I consider a plane like this? I can consider a plane like this, right? So these two OH, these two H, these two COH, because whatever the groups I have on the I have on the horizontal line, they are like towards us. And if I consider a plane like this, that is exactly dividing into two parts. So plane of symmetry is actually present. Which of the following has plane of symmetry? Try to figure out whether this has a plane of symmetry or not.
Yes, sir.
Which plane, Faizan?
From BR, if we draw the plane, it will
Yes.
divide in.
Yeah. From bromine, including bromine, if you try to draw a plane, it is exactly dividing the other two parts. It is said to be having plane of symmetry. And also you can see two methyls on the same side. So that is going to be symmetrical in nature. And the bromine atom is exactly divided into half. So this is also symmetrical in nature. Does this have a plane of symmetry?
No, sir.
Yes, sir.
No, sir. Yes.
Yes or no? Which plane?
Not, sir.
Between the two CL.
Between the two Cl, if you try to connect, are we getting a plane of symmetry? Check out. I cannot, if I try to draw a plane like this, this chlorine is above and this chlorine is below. Yes or no? And if I
Yes.
try to include one of the chlorine atom, either this chlorine or the other chlorine, then I'll be getting, like if I include this particular chlorine, this side we have carbon chlorine bond, this side we do not have, so that is not going to be symmetrical. So is there any plane? Like positions are different, right? If you have two methyls on the both down, both up, then we can say plane of symmetry is present. But this is actually towards me. This chlorine is, this is towards observer, towards, it is away. So if I try to consider this plane also, this chlorine will be towards me, whereas the other chlorine is actually away. So plane of symmetry is present or absent?
Yes, sir.
Plane of symmetry is absent. No plane of symmetry. Which of the following has plane of symmetry? So this one will have a plane of symmetry or not?
No, sir.
Yes, sir. Yes, sir.
Yes, sir.
Yes or
No,
no? So
sir.
if you try to divide the plane in this fashion, so this will cut out, like you will have this part. Bromine half, one bromine half will be there, and the other plane will be like this. Here you have chlorine half, here you have chlorine half, here you have bromine half. These are symmetrical or not?
Yes, sir.
Both are same.
Yes.
Yes or no? So plane of symmetry is present. Plane of symmetry is present. So like that, you have to draw the different planes where plane of symmetry is actually present or not. We can also look at elements of symmetry, other elements of symmetry, center of symmetry. Center of symmetry means what? Center of symmetry definition goes like this. It is an imaginary center in the molecule from which two similar groups or atoms present at opposite side are at same distance. Like it is a point in the molecule such that you start from any group. Like here one point is there, You start from group A. You draw a straight line from the group A to that particular point. Extend the straight line by same amount. Then you have to reach A again. You start from B. Like in that particular molecule, how many number of groups are there doesn't matter. From any group, if you start, draw a straight line to that particular point and extend the same straight line by same amount of length. And if you reach the same group on the other side, then that particular point is said to be center of symmetry. Center of symmetry is it is an imaginary center in the molecule from which two similar groups or atoms present at opposite sides or at same distance. If center of symmetry is present, then the molecule will also be again optically inactive. So try to figure out this molecule has center of symmetry, yes or no? Whether center of symmetry is present for this particular molecule or not.
Yes, sir.
Yes, sir.
Yes or no? This is a molecule like this. Like first check out plane of symmetry is present or not.
Yes, sir. Present.
So hydrogen is here, chlorine down, chlorine up, hydrogen down. Plane of symmetry present or not? Center of symmetry,
Present,
Yes.
sir.
center
Present.
of symmetry is that particular point. From hydrogen, if I try to draw a straight line, I'll reach the hydrogen again. From chlorine, if I try to draw a straight line, I'll reach chlorine again. From this carbon, if I try to draw a straight line, I'll reach carbon again at same distance. From this carbon also, I'm getting carbon again. So this is nothing but center of symmetry. This is nothing but center of symmetry. So center of symmetry is present. What about plane of symmetry, students?
Present.
Which
Not
plane?
present.
Which plane is the plane of symmetry? If it is present, which plane?
CL and H included.
See,
From CL and
yeah,
H.
both Cl and H, if you try to include, you will be getting a plane like this, right? You have hydrogen here. We have now I'm just considering this plane which includes hydrogen, chlorine, this hydrogen, chlorine also. This hydrogen is divided into half. So that's why I'm circling it out. This chlorine is actually also divided into half. Chlorine is actually above, hydrogen below, divided into half. Then other part, what I'm going to have? Other part will be like this. Hydrogen is again divided into half. Chlorine is also again divided into half. Chlorine here again divided into half. Hydrogen here divided into half. These are mirror images or not? Hydrogen, hydrogen matching out, chlorine,
Yes.
chlorine matching out, chlorine, chlorine matching out, hydrogen, hydrogen matching out. This is actually the plane of symmetry. Okay, plane of symmetry is also present. Plane of symmetry is also present. Center of symmetry is also present. Understand how to actually break the molecule and how to consider which type of plane. So if I give the molecule to you, first you look at the plane of symmetry and then go with the center of symmetry logics. Yes or no? So whether plane of symmetry is present or center of symmetry is present, it is optically inactive. So here in this case, center of symmetry is actually present because all are connected in this fashion. So it is a point from which if you try, from whatever the group, if you try to draw straight lines, you are getting exactly other atoms at same distance. So that particular point is said to be center of symmetry. Center of symmetry is present. Right? That is how the 3D animation goes like that further. For this particular molecule, center of symmetry is present or not?
No, sir.
No.
Sapna, plane of symmetry you have to explain in this particular case, right?
Yes, sir.
Understood? Try to break the molecule, okay? Like I'll take the paper now. You'll get clarity. See, I have paper here. So on this, in this particular paper, we have what groups? So this is carbon, carbon. To this carbon, hydrogen is above, chlorine is below. To this particular carbon, chlorine above, hydrogen below. Yes or no? Now I am breaking this. I am breaking in such a way such that atoms are also exactly divided into half. like a plane I'm considering. The hydrogen which is above, I am breaking this means I am getting one hydrogen here, one hydrogen other side. Chlorine present all means one chlorine this side, one chlorine this side, other chlorine other side. So now look at this particular plane, whatever I have cut. This carbon is included, this carbon and half hydrogen atom, this carbon also included and half chlorine. And this carbon, here you have chlorine above, half chlorine, here also half hydrogen bottom. What about the other side? Carbon, carbon and half hydrogen, carbon and half chlorine, carbon and half chlorine, carbon and half hydrogen. Look at those two. They are actually symmetrical to each other. Got it or not? They are actually mirror image to each other. Is that clear now, students? Whatever the group we have, that we are actually breaking into two halves, like two halves of hydrogen atom I have considered. So these two hydrogens are matching. These two chlorines are also matching. Both are down. These two chlorines are matching. These two hydrogens are matching. These two carbons are also matching. So I have a plane like this. That is nothing but your plane of symmetry. Got it right? Very good. Consider in this case, which of the following has center of symmetry? All of you said no. Why it is no? No center of symmetry. Why? Because we have a carbon here. Only 3 carbons are there. With these 2 carbons I can connect. But this carbon, if I try to draw any point, I am not going to get one more carbon atom. So whenever you have odd number of carbon atoms in the cyclic ring, then there is no possibility of your center of symmetry, because you cannot have the other CH2 group with respect to this particular extra one. There is no CH2 group here with respect to that particular carbon. So whenever you have odd number of carbon atoms, center of symmetry would be absent. If in odd number carbon containing cyclic compound, center of symmetry is never observed, because there is no possibility for one of the carbon which is going to be present out. Try to figure out whether this particular molecule has center of symmetry or not.
Yes, sir.
Center of symmetry present.
Center of symmetry is present. So because you can just connect a plane, all the groups in such a way such that from this particular point, if you try to connect hydrogens, CH2s, methyls, you're all having connection with the same section. All the atoms, CH2, everything is going to be connected. Center of symmetry is actually present. Center of symmetry present means optically inactive. What about this particular molecule?
Yes, sir.
Yes or no? Again, oxygens are at same distance. These carbons, this methyl above, this methyl down. So they are also found to be at equal distance. So you will be having again center of symmetry in this particular case. Yes or no? Center of symmetry is again present. So plane of symmetry or center of symmetry present means optically inactive. Optically inactive. This was the condition. Right, students? Let us proceed further.
So,
Yes, please.
sir, does this have a plane of symmetry, this compound?
You try to consider a plane. Okay, you try to consider a plane like this. This can actually divide 2 methyls exactly, but this carbon and this oxygen are not matching. Yes or no? So if I consider, like, plane of symmetry means I have to consider different planes and check it out. So if I consider a plane like this, I'm not getting a plane of symmetry. If I consider a plane like this, am I getting plane of symmetry?
No, sir.
No. If I consider a plane like this plane you try to consider. If I consider a plane
Yes.
like this, how it can be as, because one methyl is above and the other is methyl is down. I'm not passing the plane through exactly methyl. In that case, the 2 methyl groups, they are exactly half. So then there may be symmetry. But here one methyl above and one methyl below. There is no plane of symmetry. This is also not a plane of symmetry. This is not a plane of symmetry. This is not a plane of symmetry. Any other planes? Check out a plane passing through 2 oxygens now. 2 oxygens. With respect to oxygens, if you pass again methyl group, one methyl above, one methyl down, not a plane of symmetry. So there is no plane of symmetry now. Okay. Any plane,
Yes,
if you if you consider a plane passing through two methyls, then you have no plane of symmetry because oxygen atoms are different. If you are not considering a plane which is passing through two methyls, then obviously one methyl is above, other methyl is below. So there is no possibility again. So plane of symmetry is not present.
Yes, sir. Thank you.
Okay. So configuration is optical isomers. So RS configuration, absolute configuration, DL configuration, relative configuration, erythro-trio. So DL, I have told you capital D and capital N, they try to explain about the configuration. Small d and small l, they try to explain about the optical rotation. Capital D, capital L indicates optical. Capital D, capital L indicates relative configuration. Small d, small l indicates optical rotation. So as I have told you in the last class, if I have given a molecule to you like this, CH3, C, C2H5, fluorine, chlorine. How you are going to name this particular compound? What is the name of this particular compound? IUPAC name. Whatever the compound I have drawn here, students, what is the IUPAC name?
1 chloro, 1 fluoro, 1 methyl propane.
1 chloro. Are you sure?
2 chloro.
2
On
chloro,
the
2
second
fluoro.
position, right? Carbon, carbon, C2H5 means 4 carbon atoms are in the same line. So I can say on the second position you have chloro, 2 chloro, 2 fluoro,
2 fluoro. Butane.
butane. I have told you in the last class also, whatever the IUPAC name you are writing, that IUPAC name gives idea regarding the structural bonds. That is about how the structure is present, what type of substance are there, at what position they are there. But IUPAC name do not give information regarding the spatial positions. Understood this point carefully. Last class also I have told you whenever explaining geometrical isomerism. In the last class, what we have studied, students? We have studied about cis form, trans form, E form, and Z form. So before that, I used to place, if I have a alkene, I used to place cis or trans, so that I will give an idea to you how the spatial arrangement of groups is present. But now here we are not supposed to talk of geometrical isomerism because there is no C double bond system. Restricted rotating system is not there. What are the two restricted rotating systems which you have studied in the last class? Anyone? There are two restricted
Ring and
rotating
multiple
systems.
bond.
Carbon-carbon double bond and carbon-carbon single bond in cycloalkenes. Around carbon-carbon double bond rotation is not free. Around carbon-carbon single bond in cycloalkanes also rotation is not free. Whenever we have a restricted rotating system, then we can say geometrical isomerism is possible. Yes or no? Now look at this case. Here there is no geometrical isomerism possible, but there is a possibility of optical activity because this particular carbon is actually a chiral carbon. Single chiral carbon is there, optically active nature. Now this 2-chloro-2-fluorobutane actually gives idea about the structural part only, like what type of groups are there, where are they. But how are they present in space? That information is not known to you. To give that information, on the second position you have chirality, right? So instead of writing 2-chloro-2-fluorobutane, I have to write the configuration of the second carbon, whether it is R configuration or S configuration. Like 2R of 2-chloro-2-fluorobutane or 2S of 2-chloro-2-fluorobutane gives idea regarding the spatial arrangement also. So this R or S, how to assign, that we are going to study now. RS configuration is absolute configuration. Same rules, CIP rules we are going to follow now. That RRS, if you try to assign for the chiral carbon, that gives idea regarding the arrangement of groups in space. 2-chloro-2-fluorobutane gives only about structural data. If you try to write RRS, that gives the spatial information also. That will be completely naming the compound. R is nothing but rectus clockwise. S means sinister anti-clockwise. So there are some set of rules. RS configuration in Fisher projection. If the projection given to you is Fisher projection, how to decide R and S? If the projection is given to you is 3D wedge and dash projection, how to decide R and S? We are going to study one by one. If it is in Fisher projection, rule 1, Priority between the different groups attached on the chiral carbon is determined by CIP rules. CIP rules means what? Based on atomic number, you have to actually assign first priority, second priority, third priority, and fourth priority. Whenever you have a double bond, you have to consider them as two groups, two same groups connected. So priority between different groups attached on chiral carbon is determined by CIP rules. Rule 2, when a fourth priority group is present on the vertical line, if a fourth priority group is on the vertical line, then you are going from 1 to 2, 2 to 3 in the clockwise direction. Clockwise means, or always remember, clockwise if you are moving, that is said to be R configuration. Anti-clockwise means S. This is when fourth priority is on vertical line. If it is on the horizontal line, exactly reversed. If it is in the horizontal line, clockwise will be S, anti-clockwise will be R. Okay. When direction is clockwise and fourth priority group is on the vertical line, then clockwise means R, anti-clockwise means S. Yes or no? When direction is clockwise, configuration of chiral carbon will be R, and when direction is anti-clockwise, then configuration will be S. This is a rule you have to follow when the least priority group or the fourth priority group that is present on the vertical line. When fourth priority group is present at horizontal line of Fisher projection, then R becomes S and S becomes R. That is just exactly opposite. Yes or no? This is the case. If fourth priority group is on the horizontal line, then clockwise means clockwise supposed to be R, now it becomes S. Anti-clockwise supposed to be S, now it becomes R. Try to figure out, find RRS configuration for the following compounds. This is very important because I'll be giving two set of compounds to you, not the Fisher projections. I'll give two 3D molecules and ask you to figure out what are they. Then you have to figure out the configurations at every center. If the configuration at every chiral center is same, then they are said to be identical in nature. If the configuration at all the chiral centers is exactly reversed, like let us say I have three chiral centers, R, S, R is the configuration at three chiral centers, like C2, C3, C4. Okay, 2R, 3S, 4R. This is the configuration. Let us say 2 is the second carbon, 3 is the third carbon, 4 is the fourth carbon, and it is a compound one. Yeah, it is a compound one. Yeah, this configuration is just people are saying, but listen to this particular concept, whatever I'm saying. In the compound one, if the configuration at second, third, and fourth chiral carbon is 2R, 3S, 4R, and in the compound 2, if the configuration is exactly both are isomers, if the configuration is 2R, 3S, 4R, then both are said to be identical. If the configuration is a 2R, 3S, 4R, and in the second compound, if you have 2S, 3R, 4S, then both are said to be enantiomers. That means if configuration at every chiral carbon, if it is exactly reversed, then they are said to be enantiomers. If the configuration is 2R, 3S, 4R, and if you have the configuration like this, 2S, 3S, 4R, that means at one chiral carbon, the configuration has been changed, but not at all the chiral carbons. Then they are said to be diastereomers. Everyone got this or not? Whenever I have given two 3D molecules to you, everything is same. They are structural isomers. They have same structure, not structural isomers. They have difference in the position of groups only. And in that case, how to figure out whether the compound 1 and compound 2, they are identical or enantiomers or diastereomers? We have to look at the configurations at all the chiral centers. If configuration at all the chiral centers is same, then it is said to be identical. If configuration at each chiral center is reversed, enantiomers are non-superimposable mirror images. If configuration at one or two centers has been changed, but not at all centers, then that is said to be diastereomers. Got it now, students?
Yes, sir.
So to figure out whether the compounds given to you are identical or diastereomers or enantiomers, what you need to know? You need to know how to assign configuration. So that is why it is very important. So try to assign the configuration now. Fourth priority group is fluorine, because and first priority iodine, second priority bromine, third priority chlorine. 1 to 2, 2 to 3, how you are going? In the anti-clockwise direction?
Anti-clockwise.
Anti-clockwise means yes. Because
Yes.
fourth priority is on the vertical line. So anti-clockwise means yes. Answer is yes, right? Try to figure out the configuration here. Find out RRS in the following compounds. COH, CH, CH3, COH. First priority, which group? Fourth priority is hydrogen, obviously. Fourth priority is on the horizontal line, so configuration has to be reversed. First priority, OH or COH?
COH. OH.
OH.
First atom is oxygen. Here, first atom is carbon. So, based on first atom atomic number, you have to decide. First oxygen means you will have a priority. Then, obviously, COH. Then CH3. So, 1 to 2, 2 to 3. How you are going? 1 to 2, 2 to 3. Clockwise direction. Clockwise means supposed to be R, but fourth priority on the
S configuration.
horizontal. So, it has to be reversed. So, it should be S. 1, 2, 3, 4. So, it's supposed to be answer is S. Whatever the configuration here, we have how many chiral centers are there? COH. This carbon is chiral carbon or not? OH, H, COH. Chiral center. This carbon is OH, H, CO, CH3, and both are different. So these two chiral centers are there. So what is the configuration at this carbon and this carbon? If you try to give numbering, it should be 1, 2, 3, 4 IUPAC numbers. 1, 2, 3, 4, 5. So on the second and third position, you have to give the configuration because they are chiral. Try to give the name of this compound, all of you. What is the name of this compound? IUPAC name? C double bond OH, CHOH, CHOH, C double bond O CH3. 1, 2, 3, 4, 5. So what should be the name? Generally, IUPAC name, if you try to write down. Two, comma 3 dihydroxy 4 oxo 4 oxo 5, right? 5 carbons. So it should be pentanoic acid. Pentanoic acid. This is the IUPAC name without the information regarding the spatial arrangements. Now try to give the spatial arrangements. So on the second position, you have OH group, fourth priority on the list. On the second carbon, if you look carefully, fourth priority on the horizontal position. And you have first priority OH, C double bond O. This is going to be the second priority. And this will be your third priority. So 1, 2, 2, 2 to 3. How we are going? Anti-clockwise direction. It should be S, but it's supposed to be R. So on the second, you have R. So this is going to be R. What about this position? First priority, fourth priority here. C double bond O. Whereas here we have COH only. C double bond O means COO. So it should be second priority. It should be third priority. So 1, 2, 3, 1 to 2, 2 to 3. How we are going? Clockwise direction. Clockwise means R, but it should be reverse S. So R comma S. So 2R. This is 2R comma 3S. So what is the correct IUPAC name now? Including everything. 2R comma 3S comma dihydroxy 4 oxo pentanoic acid. Because the second and third carbons are chiral centers, I have given the configuration at those two chiral centers also. So what is the configuration at these two chiral carbons? R and S. So what is the IUPAC name? 2R comma 3S dihydroxy 4 oxo pentanoic acid. That will be giving the correct idea. Got it now or not?
Yes, sir.
Right? Can you take these examples? So try to do it. Homework examples. Same configuration if you try to apply. So first one will be chlorine. Already answers are given so that you can just look it at. Second one, carbon connected to bromine. 1, 2, 3, and the fourth priority is in the direction. So going in the anti-clockwise direction. Going in the clockwise direction. Clockwise means R, but here you should be having a reverse. So it should be S. Anti-clockwise direction you are going. Anti-clockwise means yes, but here it should be reversed again because fourth priority on the horizontal. Yes or no? So 2s comma 3r, that will be the correct name. So same logic you try to apply, students. For this particular molecule also you will be getting the compounds like this. That is, configuration is going to be 2s comma 3r. The configuration of this particular case is also going to be 2s comma 3r. Is that clear or not? Everything, how to assign R and S?
Yes, sir.
Yes, no? Now there are some set of rules known as interchange rules which are important. When any one group is fixed and the other three groups are rotated in any direction, the clockwise or anti-clockwise, then configuration in the molecule remains same. One group you are making it fixed, and other three groups you are rotating in the clockwise or anti-clockwise. Fluorine we have fixed, other groups rotate. If you try to fix fluorine and if you try to rotate other groups, then the configuration will be same. Like CF bond is there, carbon iodine, carbon bromine, carbon chlorine, chlorine like rotated. Iodine take the position of bromine now. Bromine will take the position of chlorine. Chlorine will take the position of iodine. Yes or no? So fluorine fixed, other groups rotate. So fluorine fixed, iodine has been moved in this direction, bromine moved in this direction, chlorine moved in this direction. Chlorine will be now here, bromine will be now here, iodine will be now here. So the configuration is going to be same. Whenever the configuration is same, what we call them? They are said to be identical or not?
Yes, sir.
So both are
Yes,
homos.
sir.
You try to figure out the configuration of these two molecules with your logics. Assign the configuration. Fourth priority is present here. First priority, second priority, third priority. 1, 2, 2, 2, 2, 3. You are going in the clockwise direction. Clockwise means R.
R.
What about here? Fourth priority is on the horizontal direction. 1, 2, 2, 2, 2, 3. You are going again in the clockwise direction. It is also R. So both have same configuration, means both are said to be identical or homos. If you try to fix one group and try to rotate the other three groups, then in that case the configuration is not going to be changed, and the compounds which have same configuration, they are said to be identical nature. That is rule number 1. Rule number 2 is, in a Fisher projection, if even number of pairs are exchanged on same chiral carbon, then configuration of molecule remains same. If you do even number of exchanges, then the configuration is going to be same, but you have to do the exchange on the same carbon. Like I have given a chiral carbon to you like this: carbon iodine, carbon fluorine, carbon chlorine, carbon bromine, and you have exchanged fluorine with chlorine. This is only one chiral carbon. You have exchanged fluorine and chlorine and exchanged bromine and iodine. You have performed even number of exchanges. In that case, what happened? Bromine iodine exchange. Bromine will go in this direction. Iodine comes to this position. Chlorine and fluorine positions are also changed. In a Fisher projection, if even number of pairs are exchanged on same chiral carbon, then configuration of the molecule remains same. That means if you do odd number of exchange, if you exchange one, if initially compound has S configuration, if you exchange one, then it will becomes R. If you exchange again, R again becomes S. So when you do two types of changes, interchanges, that means whenever you do two types of exchanges or even number of exchanges, the configuration will become same. Okay, one exchange, two exchanges. Try to figure out now what is the configuration of this particular molecule. Fourth group is present here. First, second, third. So we're going in the clockwise direction. 1, 2, 2, 2, 2, 3. Clockwise means R. So it has R configuration or S configuration.
Yes, sir.
S.
It is going anti-clockwise direction, right? 1, 2, 2, 2, 3. You are going in the anti-clockwise direction. Anti-clockwise means S. What about here? Fluorine least priority. 1, 2, 3. You are going in the clockwise direction. Clockwise means R, but fourth priority on the horizontal, so it should be S. So whenever you perform even number of exchanges, the configuration was same. So both the compounds are again said to be identical nature, identical or homos. Next rule. Arpita, there are CIP rules. I have explained that about CIP rules in the last class. I think you are not present in the last class. Just to go through that. Okay, so based on the atomic weight only, we are going to give the priority or the numbering. So based on that only, we will be getting all this. Once you watch that video, you will get the complete idea. If Fisher position is rotated by 180 degree in the plane of paper, then configuration will remain same. 180 degree means what? 180 degree rotation means, like with respect to this carbon, you have rotated completely. That means whatever the group which is above now, it becomes below. CH3 which is on the left side, that becomes on the right side. So if you try to rotate 180 degree, the COH will become down, H will go up, OH will be coming to this position, CH3 will be changing the position. So first priority, like whenever you try to rotate by 180 degree, whenever you try to rotate by 180 degree, the molecule is now going to have what? Same configuration. So configuration is not differed. So try to assign the configuration now. First priority to H, second priority to COH, third priority to CH3, fourth priority to hydrogen. So 1 to 2, 2 to 3, how you are going? In the anti-clockwise direction. And hydrogen is on the vertical, anti-clockwise means S. So 1 to 2, 2 to 3, again you are going in the anti-clockwise direction. And hydrogen fourth priority is on the vertical, so anti-clockwise means S. So both have S configuration. Yes or no? Both are homomers. Compounds which are having same configuration, they are said to be homomers. What are these compounds? Like COOCH3, CHOH, CHOH, COH. I have rotated by 180 degree, then I got COH above, OH are now going to be on the left side, H will be on the right side, COOCH3 will be on the bottom. So if I try to rotate by 180 degree, what are they said to be? Same configuration will be present or not?
Yes, sir.
Same configuration present means they are said to be again both are homomers or identical. Both are homomers or identical. Is everything clear, students, so far?
Yes, sir.
So this is how you can actually give the interchange or exchange rules in the Fisher projection, and how to assign RS configuration in wedge dash. Rule number 1: when fourth priority group is on the dash, go from 1 to 2, 2 to 3. If a fourth priority group is on the dash, then go from 1 to 2, 2 to 3. Fourth priority group should be on the dash. Then if you are going from 1 to 2, 2 to 3 in the clockwise means R, anti-clockwise means S. But if a fourth priority group is not on the dash, if a fourth priority group is on the dash, then go from assign the configurations like priority, first priority, second priority, third priority, go from 1 to 2, 2 to 3. In that case, if you are going clockwise means R, anti-clockwise means S. If a fourth priority group is not on dash position, then by even exchanges, because if you perform even number of exchanges, configuration will not be changed, right? Then by even exchanges or interchanges, fourth priority is taken on dash line and then follow rule 1. What is rule number 1? Rule number 1 is if fourth priority is on the dash line, assign the configuration, look at whether clockwise or anti-clockwise. If it is clockwise, assign R, anti-clockwise S. If a fourth priority group is not on the dash position, then you have to perform even number of exchanges. You can perform odd number. If you perform odd number, then the reverse configuration is going to be present. If you perform even number of exchanges, configuration will be same, and then follow the same rule, that is rule 1. Right? So let us apply this to 3D positions, like find RRS configuration in this case. RS configuration you try to assign for this particular molecule. Fourth priority, where is the fourth priority? Fourth priority is hydrogen because lowest atomic number. So first priority iodine, second priority bromine, third priority chlorine. 1 to 2, 2 to 3, how we are going? Anti-clockwise direction. Fourth priority is on the dash line, so it is going to be having S configuration. Yes or no?
Yes, sir.
So directly the configuration of the molecule, 3D molecule, whatever they have given, 1 to 2, 2 to 3 went in the anti-clockwise direction. It is going to be yes now. Answer is yes, and the fourth priority is on the dash line. Find RRS configuration of the following compound. This particular compound, whatever they have given to you, find RRS. How to do this? First, fourth priority should be fluorine because of it is having lowest atomic number. Fluorine is not on the dash line, so it is on the wedge line. So I have to make fluorine to go into the dash line. How we can do this? I can exchange chlorine and fluorine. So with respect to this carbon, I have to exchange even number of exchanges I have to do so that configuration is not changed. So I have exchanged chlorine and fluorine. So what happened now? Chlorine was here, fluorine was here. If I exchange only fluorine and chlorine, configuration would be reversed. So I have to exchange bromine and iodine also. So iodine was here now, bromine was here now. So what is this? Fluorine exchange with the chlorine and bromine exchange with iodine. Even number of exchanges I have performed, so configuration would be same. Configuration would be same. So now assign the numbering, like priority. Fourth priority will be fluorine, first priority iodine, second priority bromine, third priority chlorine. 1 to 2, 2 to 3. How you are going? In the anti-clockwise direction. Anti-clockwise means S. So the
S.
configuration whatever they have given to you, or the molecule whatever they have given to you, that has S configuration. 1 to 2, 2 to 3, it is going to have S configuration. Answer is S. Find out RS configuration of the following compounds. In this particular compound, what is R and what is S? Fourth priority, where it is?
Hydrogen.
Hydrogen. Fourth priority is not on the dash line, so I have to exchange. So I have to exchange hydrogen with methyl, so that hydrogen goes to the hydrogen methyl exchange, and COH I have to exchange with what? OH. So if that is the case, what happens? OH will be here, COH will be here, hydrogen will be here, methyl will be here. Yes or no, students? Now try to assign the configuration. Which is the first priority?
OH.
Fourth priority, OH is the first priority. Second priority COH. Third priority is methyl. 1 to 2, 2 to 3. How you are going? In the clockwise direction. Clockwise means R configuration. Everyone got it or not? How to assign the configuration for this set of molecules? Got it?
Yes.
Yes. You try out this one. Find out R or S configuration of the following compounds. C, COH, OH, CH3H. Sorry. So hydrogen, you have to exchange what? Hydrogen and COH, OH and CH3. If you try to exchange them, you will be having CH3 here. You will have CH3 here, and you have OH here. Hydrogen here, and COH here. So try to assign the configuration now. First priority to this particular option, second priority, third priority, 1 to 2, 2 to 1 to 2, 2 to 3. How you are going in the clockwise direction? That is going to be having R configuration. Even number of exchanges you have to perform because the configuration is going to be same, right? Very good. So then DL and configuration, D and L configuration. This is nothing but relative configuration. Earlier we have discussed about absolute configuration. This is a relative one. So D or L is applied for amino acids and carbohydrates. The basic unit for DL configuration is glyceraldehyde. So glyceraldehyde is this molecule, CH2OH, CHOH, CH3. Rules, what are the rules to apply DL configuration? Understand this carefully. Most oxidized group should be present at the top of the vertical line in Fischer production. If not present, then bring it at top by even number of exchanges or by rotation by 180 degree. Most oxidized group like COH or CHO, whatever the most oxidized group we have, that should be at the top. Maximum number of carbon atoms must be present on vertical line in Fischer production. If not present, then bring it to the vertical position by even number of exchanges. Exchanges or interchanges you have to do even number so that configuration is not changed. First point is most oxidized group should be present on the top. That is rule number 1 while you are assigning D and L. Next one is maximum number of carbon atoms must be present on the vertical line. The next one is relative position of OH in carbohydrates and NH2 in amino acids on last chiral carbon. Decide the DL naming. On the last chiral carbon, if you have OH group on the right hand side or NH2 group on the right hand side, OH or NH2 on the right hand side means D. On the left hand side, if they are present, that is said to be L. Right hand side is D, left hand side is L. Is that clear, students? Three rules are there while you are assigning DLN configuration. Rule number one is the most oxidized group, like if you have take glucose, whatever the CHO you have, that has to be assigned at the top. If any molecule like carbohydrate or amino acid is given to you, you have to keep the most oxidized carbon in the top, maximum number of carbons in the vertical line, and with respect to the relative position of OH or NH2. If OH or NH2, if they are on the right hand side, then it is D. If they are on the left hand side, they are said to be L. We have to look at the last chiral carbon. We look at some examples, you'll get most clarity. Like we have CHO, CHOH, CH2H. CHO is the most oxidized group because it is the aldehyde group. It is on the top. Maximum number of carbon atoms on the vertical line, and OH is on the last chiral carbon. Only one chiral is there. On that, OH is on the right hand side. So what is it? This is not to be D-glyceraldehyde, because OH is on the right hand side. It is said to be D-glyceraldehyde. If you have OH on the left hand side, what is that called as? It is said to be L-glyceraldehyde. Right? D-glyceraldehyde and L-glyceraldehyde. Like that, you have to assign. What is this? RCNH2HCOH. This is a general molecular formula for amino acids, if you remember. Yes or no? It is said to be
Yes.
Yes.
D amino acid. And if NH2 is on the left hand side, it is going to be L amino
Elements.
acid. So that is how you have to assign D or L configuration. Capital D, capital L refers the configuration, relative configuration. Small d, small l gives idea regarding the optical rotation. Small d, small l gives idea regarding the optical rotation, not the configuration. Find out D or L configuration of the following compound. For this particular compound, find D or L. What is it going to be, students?
D.
D. How you can say D? On the last chiral carbon, where is OH? So what are the rules I have said you? I have told you that most oxidized group should be on the top. What is the most oxidized group in this total molecule? COH. That is on the top. Yes or no? COH is on top. That is not an issue. Then you should have maximum number of carbon atoms in the maximum number of carbon atoms should be present where? In the vertical line.
Vertical.
So how I can get maximum number of carbon atoms in the vertical line? So I am going to fix this particular group as it is. One group is fixed and the other three groups are rotated. COH come to this position, OH come to this position, hydrogen come to this position. Then that can be homomer or not. Interchange rule, first interchange rule. If one of the group is fixed and the other three groups are rotated, then the configuration is not changed. So what happens now in this case? The molecule, how it moves? COH will be top, OH, H. The CH2OH come down now. OH will be moving this side, H will be moving this side. Why I have done this? Why I have done this? Because
Maximum carbons on the
maximum carbon should be on the vertical line. So if I have done this, I am getting OH on which sides?
left side.
Left hand side. So it is going to have what configuration? L configuration. Yes, sir. I have applied rule number one. That is keeping the first one rule fixed and other three groups I have rotated. If you want, you can apply even number of exchanges also. You can exchange OH and H first. Yes or no? Here also even number of exchanges performed only. So H and OH has been position changed. CH2H and H position again changed. So if I exchange H and OH, H comes here, OH comes here. Further exchange H and CH2H, CH2H comes here, H comes here. So that's what even number of exchanges also you can perform, and you can again get the same configuration, which is nothing but L. Right? Find out DRL configuration for this particular molecule. DRL.
L.
Why? Because the most oxidized positive should be on the top. So I have to rotate, I have to bring COH to the top, means I have to rotate by 180 degree rotation. So if I rotate by 180 degree, COH will be going into top, CH2OH will be bottom, and OH, OH, H, H. So OH is on the left hand side, so it should be going to have L. You don't get confused by looking at the molecule. In this molecule, OH is on the right side, so it should be D. No. Okay, you have some set of rules. Most oxidized groups should be on the top, maximum number of carbon atoms should be on the vertical line, and then if OH or NH2 on the right, then it is said to be D. If they are on the left side, then it is said to be L. Here we have applied all those rules and found the configuration was L. Yes, the same thing we are going to do. Answer is going to be L. After RS and D and L, we have erythro and trio. Same groups on same side means erythro. Same group opposite side means trio. So OH, OH, same groups are on the same side, then that is said to be erythro. OH and OH, same groups are on the opposite side now. Same groups opposite side means trio. Everyone got this logic or not? Simple. Erythro and trio means if we have same groups on same side, then they are said to be erythro. If we have same groups on opposite side, then that is said to be trio. So that is how we can actually assign the configuration for different sets of molecules. Like RS configuration is said to be absolute configuration, D and L is relative configuration, and erythro and trio based on this positions of the group. Same groups or same sides, erythro, different sides, trio. Right, students? Then comes the next concept, optical activity. How to find a optically active compound, whether the compound is optically active or not, how to find it out. So chiral carbon, if chiral carbon is equals to 1, what I have told you, chiral carbon 1 means optically active except for ring flipping.
Right.
Yes or no? Generally optically active except rapid umbrella inversion or flipping. Chiral carbon greater than 1. If you have more than one chiral carbon, what you have to do? You have to check elements of symmetry, plane of
Elements
symmetry,
of
or center of symmetry. May or may not be optically active. Check plane of symmetry or elements of symmetry. Zero chiral carbon means what you have to do? If you have zero chiral carbon, I have given the first slide itself, today's first slide. Generally optically, yeah, alkenes, biphenyls, very good. Generally it is optically inactive, but there are some set of molecules like alkenes, biphenyls, alkylidins where optical activity can be present. Alkenes mean C double bond C systems. Biphenyls means the systems. Yes or no? In alkenes and biphenyls, you can have optical activity, although we do not have any chiral carbons. Okay, we are going to start one by one. Which of the following is optically active? Try to figure out this. Can you take this as homework? This particular question, like you have to just look at elements of symmetry, like plane of symmetry or center of symmetry. If you have more than one chiral carbon, if there is only one chiral carbon, directly say optical activity, because ring flipping is only possible in quaternary amines. Right? Take this particular example as homework. Okay, tomorrow we will be continuing with our discussion. Thank you all, everyone. Bye.
Thank you.
Thank you, sir.
Thank you.